Okay, so we started the recording for today's class, and the interesting thing about the movement of the electrons, whenever they are jumping from one shell to another shell, I'll need that image. এখানে আমাদের কই জানি ছিল ওইটা exactly. Okay, beautiful. Got it. So I would want you kids to have a look at maybe this is a figure that we were talking about. This figure is not drawn to scale because drawing it to scale would require extreme amount of gap in the larger spaces and very small gap represented in the smaller spaces. We didn't want this figure to be clumped up. That's why this figure is not drawn to scale. Here the figure is energies are given in terms of e to the minus 18, and this is the primary shell or original shell of the electron. For a hydrogen atom, this is a figure for a hydrogen atom, and these are the energy levels for the upper level. What is really interesting or important for you to remember, I'm going to write this down so that you can remember this better, is that electrons jump up to a higher shell by a single jump, by absorbing energy. They can get back to their original shell by multiple jumps at in-between levels. Full stop. Jumping downward causes the electron to lose energy emitted as EM wave slash photon. Energy of this photon equals to E high minus E low. So what does this mean? What does this information mean? Let me take up this. Asha, should I work with this figure? I wanted to work with the other figure. Did we take the other figure from the Mike Randall book? Does anyone remember?
Yes, sir.
স্যার করা হয়নি।
Mike Randall বইতে এটা কত নম্বর পেজ আছে কেউ একটু বলতে পারবা? Anyone? ওটা দেখো তো, for those who have the physical book. হ্যাঁ?
ইন্ডেক্স মানে ফটো ইলেকট্রিক এফেক্টের কাছাকাছি।
এটা কত নম্বর পেজ আমি ভুলে গেছি। We're seeing diodes, we're seeing magnetic field, current field, we're seeing Helmholtz effect, velocity selection, Hall probe, magnetism, electron bending, magnetic flux, application, alternating current. There you are, photon stuff. Yeah, exactly. This is a fair dust diagram. So let me take this picture out so that I can use it for my drawing. Beautiful. So what is the part that I really want you to understand? Initially, an unexcited electron of a hydrogen atom is located at this level. This is the lowest shell. This is n equals to 1, the first shell of the hydrogen atom. If you feed a certain hydrogen amount, a certain amount of energy, this photon will go up to a certain shell by a single jump. This is very important for you to understand. It is not going to happen that electron can jump from this shell to this shell. Let's say electron makes a jump from here to here, and then from here it receives another photon and maybe goes up another shell. This is never going to happen. Electron will always make its upward jump by a single jump. But whenever it's going to coming back, it is possible that it can take an in-between jumps between the other shells. I don't know the exact reason why this happens, but this is the physical observation that I can tell. The why part, I don't know that why electrons behave in this way. So what I'm trying to mean is, let's say if we, let me get the energy differences of this one. Let's say how much would, kids, can you tell me the difference of these values? For example, this much is how much? This would be 13.6, 3.4 minus 13.6, which would be calculator
10.2. 10.2.
10.2.
I guess 10.2. Yes, sir.
আচ্ছা এরপরটা
স্যার 1.9
1.9, তারপর 1.5 minus 0.5.
So 0.65.
So thank you. 0.65 electron volt. তারপর I said wait, 17, 19, 29. 0.29. No, 0.31. 0.31 না? 54, হ্যাঁ।
Yes, sir.
0.31 ইলেকট্রন ভোল্ট, আর তারপরটা হবে হচ্ছে
0.16.
0.16. Okay. And then we have 0. So try to think about it. If we supply a certain electron of a hydrogen atom, an energy of, let's say, that is equal the a certain amount of energy which makes it to jump from the starting shell all the way up to, let's say, this shell. This is shell number 2, 3, 4, 5. Let's say it jumps up to shell number 5. Now the electron, this is the amount of energy that electron has to be delivered to make the upward jump. This will happen in a single step. So to make this happen, the electron would require to be supplied. I mean, I said that this was supplied. Now let's, if we talk about that, how much energy would be required by the electron to make this much jump possible. You can simply add up the energy gaps in between. So we're going to add up this amount of energy plus this plus this plus this. So we're going to add up four numbers: 10.2 plus 1.9 plus 0.65 plus 0.31. If we add these numbers, I seriously need to get my calculator. All right, I found my calculator. Ah. So if I sum up these numbers, 10.2 plus 1.9 plus 0.65 plus 0.31, I'm going to get 13.06. So to make a jump for a certain electron to go from this level to this level, the energy of the photon needed to be supplied would have been 13.06 electron volt equivalent of an amount of energy. Now, let's say the electron is located at 1, 2, 3, 2, 3, 4, at the fifth shell. From the fifth shell, it will immediately start to come down, but it can take multiple steps in the process of coming down. So it is possible. So what are the likelihood, or what are the likely possibilities for this for individual pathways for this jump to happen downwards? I'm going to use maybe purple, this dark blue color using a sharper line. I'm going to show. Now I'm going to show you downwards line. So the electron can make its jump directly from the fifth shell to the bottom shell. This is possible. Zoom in. The electron can make its journey directly from the fifth shell to the fourth shell. It can make fifth to third, it can make fifth to second, or it can make its journey in a single step going all the way from the fifth to the bottom. It can make either of these jumps. However, whenever the electron makes its jump over here, it's not essentially going to stay there. But then again, from the fourth shell, if I try to draw, it can jump to 3, it can jump to 2, it can jump to 1, and then from this one as well. I think you are already getting the pattern of here, that what is happening here. So all of these are the possible size of the jumps of the electron itself if it is about to come downwards from the shell number 5. So it can take individual jumps. It can take 5 to 3 and then from 3 to 1, or it might as well take 3 to 1. So it can take 5 to 2 and then from 2 to 1. So it can take multiple different jumps, but each of these individual jumps would correspond to a certain photon emitted. So whenever the electrons are jumping upwards, they're absorbing energy. This is energy absorbed. This energy absorption doesn't necessarily have to be from photons. This can be supplied by heat energy as well. It can be supplied by electrostatic energy as well. So this is, so going upwards is energy absorption. Absorbed. This is energy absorbed. And then whenever is all of this electrons are coming downwards, energy or slash photon will be given up. So we can calculate exactly what color of photons are we going to get for a certain amount of energy. For example, if it so happens that the electrons make a jump from, I'm going to write this thing over here so that you can make a better understanding. Let's say if I tell you that in this case, This electron is going to make a jump from 5 to 3 to 1. This is the jump that is happening. So you might be asked that what is the corresponding frequency of the electromagnetic wave? What is the corresponding frequency of the electromagnetic wave? So we can calculate this pretty simply. Have a look. If the electron jumps from 5 to 3, the energy value for shell number 5 is this one. I might as well label this because this is actually a bit tilted. Labeling means this is relevant to this one, this is relevant to this one, and this is relevant to this one, and that one is 0. So I just wanted that to be labeled. So whenever the electron is going from 5 to 3, we have to subtract the energy difference of those two values. So shell number 5 এর 1 2 3 4 5 shell number 5 এর energy value হচ্ছে -0.54, and shell number 3 এর energy value হচ্ছে -1.5. So -1.5. This is the amount electron volt. This subtraction gives us how much? 1.5 minus 0.54. Hold on, calculation গুলো আমার সাথে করতে থাকো. Don't just wait up for me to do the calculation so that if
Sir, 0.96.
yeah, so that if I'm mistaken, you can actually help me correct them. So this is going to be 0.96 electron volt. We're going to calculate out how much energy this is on the right side, but I got me energy calculate. This is for the jump from 5 into 3 for this one. Then whenever the electron will make a jump, another jump from, let's say, 3 to 1, then the energy variation will be minus 1.5 minus 3.4. Now 13.6, sorry, 13.6 electron volt. This would be how much? 13.6 minus 1.5.
12.1.
12.1 electron volt. So these are the two individual photon energy values which will be emitted. Maun, আমাকে একটু কফি খাওয়াবা? Normal coffee খাওয়ালে হবে. This is the amount of energy which we're going to get, photon values we're going to get from these two individual jumps. Now you can try to calculate what will be the relevant frequency for these two energies. Now here comes the photon calculation. E equals to hf. This is the energy of a photon, Planck's constant. F is the frequency which I am trying to find out. Here the energies are given in electron volts. These are not given into joules. But if you want to get the absolute frequency in hertz, you have to place it in joules. So I will have to convert this into joule as well, which I'm going to do. Don't worry. The value of H is given by 6.63 into 10 to the power minus 34 joules second. You don't have to memorize this value. I just remember this because I have used it too many times. So I remember this just by using it too many times. This is the Planck's constant which will be given to you in the formula sheet. So you don't have to memorize this number at all. So if I want to calculate out the possible frequency out of this number, I can write that this is the amount of energy, 0.96. To convert the electron volt into joule, I simply have to multiply this by the numerical value of 1 electron's charge. So 1.6 into 10 to the minus 19 coulomb, which is the charge value of an electron, or we call it elementary charge. This is the amount of energy. So now this whole thing has converted into joule, equals to 6.63 into 10 to the power minus 34 joule second. I'm writing the numbers as well to give you a better idea for how the equation is going to pan out into frequency. So এখান থেকে দেখো আমাদের both sides joule গুলো কাটারে চলে যাবে, and on the left side we're going to have second inverse 1, which is basically hertz. So if you do the division right now, how much frequency are we going to get? Standard form 0.96 into 1.6 10 to the power
2.32 into 10 power 14, sir.
I would like to include this value. I don't want to be mistaken as I go down the line. I'm pretty sure about this value, but I just want to make sure of it real quick. Go to any question paper and we can find out this value in the formula sheet. Planck's constant 6.6. Here, I'm good. So এটা কত আসছে? 1.54.
Sir, 2.32 times 10 power 14.
আচ্ছা আমি মেস আপ করে ফেলছি आंसर. Why have I become so inefficient in using calculators? 2.32 into 10 to the power minus, minus now, 10 to the power 14. 14 hertz. So this is the color that you're gonna get. And if we go for this calculation, it's pretty much the same thing. So this would be 12.1, blah, 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 blah. And so what frequency are we gonna get from here? That answer divided by, no, hold up. এটা করে দেখা কত আসে?
2.92 10 to the power 15.
Sir,
2.92 10 to the power 15, yes.
আচ্ছা স্যার এইচ কি সবসময় কনস্ট্যান্ট থাকে?
It's called Planck's constant.
ম্যাক্স প্ল্যাঙ্ক হ্যাঁ
Called Planck's constant. It's a natural constant. Currently, the unit of mass is defined by Planck's constant. Happened last year. Do you guys know that
আর স্যার
1
ইলেকট্রন
kilogram is not defined as the block or as the mass of that cylinder anymore? 1 kilogram is now defined as in terms of Planck's constant and Avogadro's constant. These two things. Yes, bolo.
স্যার বলছিলাম যে ইলেকট্রন ভোল্ট থাকলে জুলে কনভার্ট করতে গেলে বা এনার্জিতে কনভার্ট করতে গেলে ইলেকট্রনের চার্জ দিয়ে মাল্টিপ্লাই করতে হবে, রাইট?
Yeah.
আচ্ছা
So this is the total calculation. That these are two different colors we're gonna see. Now, interesting for us so so this is the type of calculation that we're gonna be doing. We'll be asked to do for our calculation for most part in the worksheets. But the reason I'm trying to show you is that hydrogen atoms, I mean, the electron of the hydrogen might not as well go to level 5. It might as well go to level 3, and it is possible that this electron can make its jump directly to the shell number 1. If it makes it jump in a single stage, for example, this line, it is possible to get all the energy in a single photon. Which will be the highest energetic photon out of this process, out of this excitation. Now, what happens that if you have, let's say, a lump of hydrogen gas, and you are beaming them up or you're heating them up, and at one point the hydrogen gas is starting to glow. What's going to happen that you do understand that hydrogen is not going to give you all the continuous variation of frequency like the sun we receive from the sun, the entire spectrum of the rainbow colors. It is going to give us some very discrete values of frequency depending upon how much jump the hydrogen electrons are making, and as they're coming back, they're going to give up a certain amount of photon, which will necessarily be relevant to some specific frequency of color. This is the behavior that we use, or this radiating out a specific frequency or specific value or discrete values of frequencies give us the emission spectra. Now I'm gonna describe about emission spectra in a while, but this is what gives us the emission spectra. Emission spectra is basically the characteristics wavelength output out of a atomic stage of an element whenever its electrons are heated up enough, and then they are allowed to come back to the original shell. This is also pretty much the basis of flame tests. For example, if I show you this video over here, this area over here, this is the typical the sun spectrum show some dark lines. No, what? Acha, I was about to talk about this thing. So let's have a look at this one. The idea is that this is a full spectrum, like the entire white light divided into all the continuous variation of frequency of colors. This is the whole spectrum. And if we have some very specific element heated in this manner, and then detect all of their individual colors and make another behavior like this. So this figure, I mean, this is a type of figure that you will not be essentially seeing. You will not be essentially seeing to exist. Beautiful. Yes. So we're not gonna see this kind of behavior over on a dark screen. It is just a mathematical plotting of the specific color at the specific color's positions. For example, if you see over here, on the very left side, we're gonna have a very high frequency, violet, purple, this range. On the very right, we can have a pretty low frequency because it's almost reddish. So let's say a certain element gives us this specific shines of color whenever it is heated to a very high temperature, which means its electrons are capable of giving us photons which respond to these exclusive colors. It might be for another element, it might be this one, for another element, it might be this one. So different. So you can see over here, they have actually said that spectra of a white light, the whole thing is available, and light from mercury. Mercury gives us this kind of pattern. So you can see that there is not only one single light wave, because it is possible when the electrons are coming down, they can make multiple jumps. And you can see over here we have a very, very dim yet visible high frequency light. The reason this light, this beam being so dim is that the number of electrons, statistically speaking, which are gonna make the jump directly from the highest shell to the ground level is gonna be really, really few. For example, let's say if you have 1 million particles, maybe even 0.01% of those atoms might actually give you the whole jump. So the intensity of that specific color of it would be very, very low, but it would be detectable. So that's why we have a really dim line which lies on the very highest range of the frequencies. However, if you observe the brightness of all of these lines, this line appeared to be the most bright, which means this will be the most prominent color if you do the flame test for mercury. Because all of these colors would actually get merged together whenever we'll be seeing by our naked eye, and we'll get a combined sensation of all of these colors. So this bright yellow, which is really most prominent jumps. For example, this jump might be for one of the shell, and most electrons for mercury who are doing this amount of jump. So they are giving us that amount of energy photon, which is happening so many times, which is happening far too often compared to the other jumps of the atoms. And as a result, this would be the prominent color in the mercury's emission spectra. B is for helium. Helium gives us a lot of spectra, and D is for cadmium vapor. So we have a lot of different. I'll give you floor. So we'll be having this kind of variation for different spectra. Now, these different individual line things, these are what we call the emission spectra. Emission spectra are always line spectra because we get multiple different lines in the designated wavelength region. So if you have a look over here, we'll now look at another phenomenon which can be explained in terms of the light as photons. We rely a great deal on light to inform us about our surroundings. Using our eyes, we can identify many different colors. Scientists take this further by analyzing light, by breaking or splitting it up into spectrum. The technical term for the splitting of the light into its component is called dispersion. This is a scientific term, not important for your syllabus, but additional knowledge, not bad. You'll be familiar with the ways in which this can be done. Using a prism or a diffraction grating, the spectrum of white light shows that it consists of a range of wavelengths from about 4 × 10⁻⁷ meter violet and about 7 × 10⁻⁷ meter red, as in figure 3.0212a. This is a continuous spectrum. So this is what we call a continuous spectrum, where we don't have any missing parts. It is more interesting to look at the spectrum from a hot gas. If you look at the lamp that contains a gas such as neon or sodium, you will see that only certain colors are present. Each color has a unique wavelength. If the source is narrow and it is viewed through a diffraction grating, a line spectrum is seen. Figures 30.12b shows the line spectrum for hot gases of the elements of mercury, helium, and cadmium. Each element has a spectrum with unique collection of wavelengths. Therefore, the line spectrum can be used to identify elements. This is exactly what the British astronomer William Huggins used when he did this. Okay, so what is happening over here? This is the white light, which was split up into its continuous spectrum, and we can have this whole thing for the output. So this is what we call the emission spectra, which is coming out as a line spectra. The other thing that we can have is called absorption spectra. I'm going to explain absorption spectra after a while, but at this point, I'll take some questions. Abhiaz, you raised your hand long ago. Go ahead.
Sir, on the thing of the energy levels, the line with the zero electron volt, is that shell number infinity?
Yes, that's shell number infinity. Physically, it is shell number infinity means it is that far away from the atom. Physically, that distance away from the atom that the atom has no more attraction on that electron anymore. It is not physically infinite distance away. It is the electron is chemically free from the attraction of the atom. That is the shell that we define as shell number infinity. It's not. It doesn't have to be infinitely away, because you can see over here that as where is that figure? you can see over here, as we have calculated this energy difference, you can see that the energy difference is slowly becoming less and less and less. Do you see that?
Yes,
So
sir.
really large and smaller, smaller, smaller. So the farther we go up in the energy level differences, the energy differences become so low. So there comes a certain point where the energy may be
কম্পিউটারের প্রবলেম কি ভাই?
yes, the computer might have some problems. No, Shubho, the computer might have some problems. Wait, আচ্ছা যেটা বলতেছিলাম সেটা হচ্ছে I cannot mute Shubho.
স্যার কিছু একটা প্রবলেম হয়েছে ইয়েতে, এই কারণে আর কি।
আচ্ছা ও আচ্ছা anyway যেটা বলছিলাম সেটা হচ্ছে as we go further away from the in the shell, the increased number of shells will have really minuscule amount of energy difference between them, and as a result the n equals to infinite is actually pretty close compared to the atom in terms of our measurement, but not in terms of atoms measurement. So that is infinite number shell where the energy value is 0, or that is the closest position where we can say that the electron is absolutely free from the atom. Abhias, did I answer your question?
Yes, sir. And another thing, sir, about the colors, how are they produced on the line spectrum?
Oh, these colors are produced whenever the here's the deal. Let's say we are trying to heat up hydrogen. We are providing the hydrogen from a heat source, and the electrons are allowed to jump pretty high above, and eventually they can jump backwards. You have to understand that this is the energy values for hydrogen. For helium, all of these values would be different. For any other element, all of these values would be different as well, because we can only have the electrons jumping from the outer shell layer into higher level. For hydrogen, we can have that jump happening from the shell number 1 above, but for above helium, you cannot have that. But for helium, you can have the electrons jumping from their first shell going up and down. Yeah, for helium, we can actually do that actually, but above helium, we cannot do that, because for example, hydrogen, helium, lithium. I think for lithium, the only electron that is capable of jumping up or giving you different color is the second shell layer electron, because the first shell layer electrons are not going to make any jump. They are pretty much stable in their first shell. So these numbers are going to be pretty different for different elements. So whenever you provide enough energy for the electrons to be excited and go into their upper shell, they can make this jump upwards. But as they will come back, for reasons I did not explain, and I do not know, honestly, I didn't study about this, they can make multiple different jump sizes, which I described over here. And based upon those jump, you have to understand that each of these jump has a very specific amount of energy emitted for the photon. Each of those energy will give those photons a very characteristic frequency calculated by E equals to HF. You cannot have all the photons from a specific element, because its own shells are arranged in a certain way, which is very unique for its own characteristics.
So for very specific values of energy, sir, very specific frequencies of light are emitted.
Precisely. But it can be measured, or not measured. I mean, what I can say that it can be, we can understand that because the reason we are having discrete values of photons emitted, because the shells are not continuous. Electrons can have at discrete shell values.
Yes, sir.
Yeah, Hamza, you have a question.
Sir, I think I missed something.
Which part?
The shell energy level for electrons that relate to colors, because colors are dependent on frequency and wavelength.
Yes.
How does that relate? I can't get that.
Whenever the electrons will be excited, they will absorb the energy and go to a higher shell. Immediately after, they will start to come back to the original shell, or they will become de-excited. Whenever they will become de-excited and come to the original shell, they will give up that absorbed energy as electromagnetic radiation. So it's something like this. Let's say an electron is over here, just for without this term. মনে করো ইলেকট্রন এখানে আছে, সে 100 জুল এনার্জি অ্যাবজর্ব করে এখানে উঠলো। এখন মনে করো এখান থেকে সে যদি ডিরেক্টলি আবার অরিজিনাল শেলে ব্যাক করে, তখন সে এক্স্যাক্টলি 100 জুল অ্যামাউন্ট অফ এনার্জি গিভ আপ করবে। That giving up of energy would happen in the form of a photon. So it will basically radiate out that amount of energy that it absorbed from any physical source. Thermal energy হতে পারে, সেটা electrostatic energy হতে পারে. So the input energy can be of different form, but whenever the electron will come back to its original shell, this will give away that absorbed energy as photon or electromagnetic wave.
Okay, so I got it.
বুঝে গেছে? So
Yes,
interesting
sir.
পার্টটা হচ্ছে emission can only happen when the electrons are de-excited or they are coming back to their original shell. Going upwards এর জন্য কিন্তু কোনো ইলেকট্রন এমিশন কোনো ফোটন এমিশন হবে না। আপওয়ার্ড রাইজের জন্য energy absorbed হয়. So colors or line spectra or emission spectra are only possible once electrons are de-excited. This is the important part. The other thing that I'd like to discuss for over here, what we have over here is an absorption spectrum. And absorption spectrum is pretty interesting. Absorption spectrum basic idea হচ্ছে আচ্ছা আমি absorption spectrum এর use টা আগে বলি so that it will be much more too easier for you to perceive the idea. The purpose of an absorption spectrum is to primarily detect the presence slash the specific elements which are present in a certain compound that we might not know. For example, let's say a meteorite landed on Earth. Well, obviously, it burned a lot of its parts as it passed through the atmosphere, but let's say some solid part of a meteorite lands on the Earth, and we want to know what are the constituent elements of this meteorite. So what we can do, we are going to take a small chunk of it, then we're going to make it into very fine powder, and then we're going to make it into super fine powder, and then we're going to make it into extreme superfine powder so that it will become nearly atomized, like, or at least in molecules. It will be so small, each of the particles will be so small that it will be in very, very, very small powder format. Then we're going to spray some of those powder into a vacuum chamber. So let me just draw this thing for you to visualize. Let's say this is a vacuum chamber. We have sprayed some of those meteorite powder over here, or this is actually molecular level, or they're extremely small, and we have made sure that this thing is highly vacuum, or if it is not, we are going to fill it up with a known gas. For example, first what we can do, we can fill up this entire chamber, replace the entire atmosphere with a known gas that we know. For example, like we can fill it up with maybe no, vacuum is good. We're going to keep this vacuum and we're going to spray these particles. And then from this side, we're going to send white light into this chamber. And on this side, we're going to have a detector which is going to detect that which of the light are essentially, as they is passing through, and which of the light will be detected over here. Now, there happens to be an interesting thing. Whenever white light will be sent through this chamber, and here we'll have the detector, all the elements which are present in these gas particles, they will absorb light waves or photons from the white light source that is convenient for them to absorb. This will happen not essentially by 100%, but the intensity of the light will be reduced. What I'm trying to say is that if we are sending a white light of, let's say, 100% brightness of all the individual colors, and let's say on the receiving end, we are missing out on some very specific frequency. Maybe let's say the entire violet region is quite 100%, which was unabsorbed in this whole container. But let's say certain frequency, let's say violet is 4, so let's say 4.1 × 10⁻⁷ meter. This frequency got reduced to a brightness of, let's say, 50%. But everything above and everything below has the same brightness, which means this light or this wavelength of light or this specific frequency of light or these energetic photons got somewhat absorbed in these elements. Now we can make an absorption spectra depending upon which of the lights which lost their brightness or which got absorbed. We can draw up a figure that can look like this. Here they have shown the absorbed light as perfectly black lines. So we, in all the places we have missed out some lights or some lights got absorbed in that absorption chamber, we have some black lines, which means these are the lights which did not get absorbed, which you can see in full brightness. All of these black lines represents some part of the light which got absorbed within this component. Now, this tells us exactly which of the elements might be actually present here. So what we can do, we can start reading of this chart from the very left and slowly record that exactly which are the at which wavelength values did we have absorption. Then we will compare this figure with multiple of the known spectra of the elements. For example, hydrogen have one set of element or line spectra, then hydrogen, helium, lithium, barium, boron, carbon. If you think about it, all the individual elements that we have, we know the individual line spectra. These line spectra represent the corresponding wavelength of those elements whenever they are excited and they are emitting out photons. But here they were not excited, rather they were allowed to feed on the photons. That's the difference. So we made them into very fine powder, and then we send the white light spectrum, which have all the individual photons, and now we allowed the atoms to absorb those photons. So many of those atoms would absorb those photons, and if you wonder, well, what happens when they absorb these photons? Well, this is the thing. They might actually absorb those photons, and they will essentially give up those photons immediately. This is obvious because electrons are not going to hold on to that energy forever. But that radiating out of that energy might happen in a random direction. For example, here all of the white lights were sent in this manner. But let's say here is a certain atom which absorb this color, an electron which absorb this color, this specific photon. Then it's going to de-excite and give up this photon, and that radiation outwards can happen in a lot of different angles. It doesn't necessarily have to happen in the exact horizontal direction. So you are basically having a missed amount or reduced amount of brightness of this color of light as a white light is passing horizontally, because this light is going to get dispersed in other directions, because electrons are not going to hold on to the energy forever. They absorb this energy, they excite, and they immediately get de-excited, and they eventually give out that energy into other different forms. So we are going to measure exactly what are the missing parts over here, and we're going to compare this with a lot of the known line spectra that we have predetermined from our experiments. And comparing those figures with this part, we can actually find out which are the elements which are present over here. So let's say we have a pattern over here. Let's say we'll take the behavior for this is cadmium vapor. So let's say we take this one, and if we place it up over here, and if we see that this cadmium thing actually fills up multiple different locations on this figure, then we can say that, well, cadmium was present in this specimen, because we can see that all the light energies, all the photon values that cadmium is supposed to give up, those things are missing over here, which means cadmium is present there because cadmium atoms did absorb those specific photon values. And we can now place another one for the other lines, so we can overlap multiple different element values to ultimately artificially create this whole thing. And that we would know what are the exact elements which are present in there. So this helps to find out the exact composition of a certain element, not to their atomic, not to their molecular bonding, at least to know what is present there. That helps for that. I'll take questions. Abiyaz.
Yes, sir. This process is reverse of the providing energy for the elements to emit light.
Exactly.
Here you're giving light and they're absorbing the energy from the light, and we're seeing what frequency of light is getting absorbed.
Yeah, precisely that.
Okay, sorry.
So that's that. And as for other stuff, what we can think about, that's pretty much it for this part of the calculation. We're gonna see some calculation about those, but this is the basic difference between line spectra and the emission of the line spectra and everything. So here we have some of those calculations that they're trying to show you regarding these parts. You can essentially read these things. If any of the calculation doesn't make sense, you can ask me about them. So they're showing that when the photons are emitted from here. So going up is, so what they are showing in this case, I believe, is that we are sending multiple different photons through a certain element. The photon that perfectly matches with a certain gap will be absorbed by the electron, so that it can make that jump. It will not absorb a random amount of photon. It will absorb a fixed amount of photon, which is exactly equal to its convenient jump size. So other photons will not be absorbed. This is basically what happens in the absorption spectra behavior, that they absorb the photons which are convenient for them to make a convenient jump from one level to the higher above level. And here they have shown us some of the calculation which I just showed you, which is pretty good. And here we have some idea for the forbidden gaps or the shell boundaries. This is a part of your AS level thing, band theory and elliptical conduction. You kids might have read this part. And then comes the de Broglie wavelength. Yes, this will be the next topic that I'm going to pick up, but I'll take questions now. Yeah, Rafid, go ahead.
স্যার এই যে আপনি যে দেখালেন ফর দ্য অ্যাবজর্পশন স্পেকট্রাম, তো এখানে কি আমরা কনসিডার করছি যেগুলো অ্যাবজর্ব করে জাম্পটা মেক করবে দে আর স্ক্যাটার্ড ইন অল ডিরেকশনস, দ্যাটস ওয়াই ওগুলা ডিটেক্ট করতে পারছে না।
Yes,
বাট স্যার স্টিল তো অল্প কিছু মিনিমাল অ্যামাউন্ট তো এদিকে ইয়ে করবে।
exactly, exactly. করবে. But the thing is, the reduction of the brightness of that exclusive frequency / wavelength will be significant compared to the other. It might not be altogether zero, because we are sending a pretty bright light through that powdered or pulverized specimen. So it will not be essentially become zero, but it will be reduced significantly.
স্যার আরেকটা জিনিস ছিল যে লাইক ইজ দ্যাট পসিবল দ্যাট while it's coming back it can release more than one photons to make a single jump, to make a single comeback to a lower level shell?
So from a energy from an excited level, it is coming directly back to its original shell and releasing 2 photons.
মানে সাইমালটেনিয়াসলি দুইটা একটার পর পর, নাকি সবসময় যে একটাই রিলিজ করবে?
No, it's about the jump size. For example, what I'm trying to mean, let's say, আচ্ছা আমার তো এটা লাগতেছে না, হয়ে গেল বলতেছি আমি just a second. মনে করো, let's say an electron has jumped to, let's say, shell number 1 to 3. Let's assume the electron has jumped to shell number 3. If it directly makes, মনে করো shell number 1 এবং shell number, let's say the energy difference between shell number 1 and 3 is, let's say, 20 joule. Now, if this amount of gap is 20 joule, then if the electron makes a single jump, then it will give up a photon of 20 joule worth of photon. But if it makes multiple jumps, then each of those photons would be smaller than 20 joule, but the sum of the energy would be 20 joule as well. So it is basically not, we are essentially trying to determine that exactly what values of photons are released from that specimen. But answering your question, that if it makes a single jump from the excited stage back to its original shell, would it be possible for it to emit out two photons? The answer is a no. Every individual jump downwards corresponds to one emitted photon.
Sir, so for each consecutive jump, like a photon is emitted.
For each jump from one shell to the downward shell, 1 photon is emitted. Yes.
But if it's a direct jump from, let's say, 5 to 1 or 5 to 2, and only one big photon is released.
Exactly, and that happens pretty less often. That's why we had such a very dim line over here, because that's not very prominent. That's not very common, but it can happen for certain electrons. Rafi, did I get your question answered?
Yes sir.
Okay, Mugdha, go ahead.
স্যার মানে স্যার যেখানে লাইন স্পেক্ট্রাটা সবচেয়ে ব্রাইট, ওখানে কি ইলেকট্রনসটা সবচেয়ে বেশি এক্সাইটেড অর সামথিং?
No,
or why are they so bright?
the brightness of these lines are relevant to how many of these photons are available. So if a line is very bright compared to another one, you have to understand that those photons were produced in bigger numbers compared to the photons of the dimmer line. So most electrons made that jump. For example, over here, this yellow line is really bright, which means nearly most of the electrons, or significantly large number of electrons for the for the mercury atom, made this jump in their coming downwards. Very few of them made this, very few of them made this, a bit bigger number made this, even a smaller number made this. So the brightness is relevant to how many photons were released of that specific energy amount. Brightness is relevant to the number of
photons. This is basically the number of electrons.
Sorry,
the number of electrons which made the jump. Sir?
Yes, the number of electrons that made the jump.
and emitted a photon.
Yes.
Is it that? And
The
sir, our absorptionের সময় yes sir, continue sir.
না না বলো বলো আমি শুনতেছি you what you said is perfectly correct and go ahead.
And sir, absorptionের সময় the electrons absorb some portion of energy and emit a photon themselves.
Yes. But they only
Okay, sir. Thank you, sir.
But they only absorb in the case of absorption, they only absorb those photons which are convenient for them to make a certain jump from one level to the above level, something that is shown over here. For example, if you are sending a photon that has an energy from here to, let's say, up to this much level, that photon will not be absorbed by this element. If you are sending photon which is up to this size or which is up to this much size, exactly matches the gap size of the two bands, then that photon will be absorbed. But other photons which does not match the gap in between will not be absorbed. They will simply pass through. Those electrons would not even take those photons because they cannot make a logical jump absorbing that photon.
Yes, sir. Thank you, sir.
Sure. So the next part that we have over here is the nature of light or wave particle duality, which brings us to the interesting part of the quantum physics. Is light a wave or particle? Well, there are many different ways to describe this, but there is a simple version that I have taken into my brain when I was a student, and I've been teaching this to my students for a pretty long time. The thing is, if you think for the behavior for reflection, think of the idea of a reflection for a physical object. If you throw a tennis ball to a wall at some angle, it will bounce off at equal reflection angle. So behavior of reflection is something that is pretty much related to particle behavior. Lights show perfect representation of reflection. Reflection, on the other hand, is a behavior that is not relevant to solid objects. For example, if you shoot a bullet into water, that bullet is going to slow down, but it's not going to change direction. But light, as it enters from one transparent medium to another transparent medium, at the boundary level, it actually changes direction, which is a perfect representation of its wave behavior. The spreading out of light as it comes out through a hole is a perfect behavior of wave. The photoelectric effect is a perfect behavior as a particle. The problem is that if you set up multiple different experiments with lights, where they will have to show both of the behavior. For example, let's say you send some light through a diffraction grating of a monochromatic light frequency, and beyond on the receiving end, you place some photoelectric specimen, for example, some metal which is capable to give a photoelectric effect. It is going to show you simultaneous behavior of diffraction, which means bending through the gap, and then on the receiving end, it will give you photoelectric effect. So interesting enough is that the light can behave, light does behave as wave and particle both. Depending on what behavior you're observing, it can give you that behavior. If you're observing, let's say, photoelectric effect or reflection, you can say light is a particle. If you're observing reflection or diffraction, you can say light is a wave. So light can work as a particle and wave both, but what behavior are you going to see depends upon what experiment are you dealing with. Now comes the interesting part, is that this is the second experiment, second equation, lambda equals to h by p, de Broglie equation. De Broglie equation or de Broglie equation. I'm not sure how to pronounce it. I might as well find this out right now. I think it's de Broglie. I think the G is not pronounced.
De Broglie.
De Broglie, okay. All right, so this is the de Broglie equation, but spells like this, Broglie. So de Broglie equation, and this is the equation that is lambda equals to h by p. This is a really, really, really interesting equation. I'll show you why I find this equation fascinating. Have a look at this equation first. Do you guys recognize this equation?
Sir,
What is this?
Similar, sir. It looks similar.
Einstein.
Can put my finger on it.
This is the energy conversion equation for Einstein's special theory of relativity, equals to mc squared, which converts mass into energy. They're not supposed to be convertible. At least they didn't used to be convertible before Albert Einstein showed us this equation. But then we came to know that no, energy and mass are not conserved units, they can be interconvertible. Interesting. We know this equation. This equation is very famous because bombs were made out of these equations, world got destruction out of this equation, so this equation is pretty famous. On the other hand, I have de Broglie equation, lambda equals to h by rho. Lambda means wavelength, wave behavior. H is a Planck's constant, which is a constant of nature. P represents momentum. Momentum essentially means mass h divided by mass times velocity. So here you have mass, here you have wavelength. So this is showing that something can be considered as a wave and mass alternately. These are the two equations which actually merges these two worlds of physical mass world and the energy world or wave world. This equation is not that famous because bombs were not made out of this and people were not killed. That's what I think. So this is the de Broglie equation, which means that the physical significance of this equation is that every object having some mass, if it is moving, would be relevant to some wave behavior. Every object have this wave characteristics. So lambda equals to h by rho. So let me write this thing once again with constant 6.63 into 10 to the power minus 34 m into v. So any object with mass will have a wave behavior or representation as a wave that we can calculate out of this equation, and it is experimentally provable. But what is bothersome, okay, what is bothersome is that, I mean, not bothersome, so before I get into the bothersome part, this essentially means that if I am a mass of, let's say, 70 kg, conservative value, and I'm moving at 10 meters per second, this equal value would be 700, 70 to 10. So I would be having some wavelength that can be calculated from this value, but that value of wavelength would be extremely small to be even measured, to be even observed. We can essentially see that this wavelength at a measurable value by our equipment that we have developed as human species, only if this value of MV is extremely small, so small that this ratio would give us some number, measurable number over here. So bottom line, the wave behavior for physical masses is actually visible for extremely small objects which have such a small mass that this thing can have some value. For example, if I replace this equation for electron, if I write the equation 6.63 10 to the minus 34, which is the value of Planck's constant, mass of an electron is 9.1 to 10 to the power minus 31 kg. Now, if we have the mass of an electron at, let's say, half the speed of light, or maybe 10% of the speed of light, so let's say 0.3 into 10 to the power 8. So you can see that this equation can give you a significant measurable value for the lambda, which means electrons wave behavior can be observed by our equipment setup, and that's essentially what is going to come up as our next part of the demonstration. So here it comes. This is de Broglie. So this is the whole description over here. He received a Nobel Prize in 1929. And then electron diffraction experiment, it goes like this. Let me tell you what is happening here. So let me use this figure. Here we have an electron gun. We have the 6-volt harmonic emission point. This is 0 volt. So this coil is heating up. This is a 5 kilovolt tunnel, which is the accelerating voltage for the electron. So this part is actually working as an electron gun. Here we have a graphite. Now, this graphite is actually very thin, or we can actually call it a graphene sheet, if you kids have known this thing. For those of you who have chemistry, you know that the graphite actually makes a hexagonal sigma layer, which are joined with other sigma layers by vertical pi bonds. So each of these sigma layer has a hexagonal structure between them. So physically thinking that between all of those hexagons, there is a hole. Between all of those hexagons, there is a hole. Whenever an electron gun is shot through a very thin graphite sheet, it is seen that electrons do not go in a perfect straight line. Rather, they spread out like waves do spread out whenever they go through a tiny hole. So each of those hexagonal hole of that graphite piece or graphene sheet work as a single piece hole through which when the electrons go by, they take deviation like waves would. And how much deviation would they make can be seen in this circular pattern. So this is actually a fluorescent coating that we have on this side of this flask, and we are shooting a single line of electron over here. Here we have the graphene sheet. This part is actually basically the reflection of this thing coming from the back of the spherical chamber of air. So forget about this part. This is not relevant. This is just a reflection. Actually, we have the electron gun over here. We have the graphene sheet over here, which is slightly illuminated over here, and the electrons are making circular patterns like this. This pattern can be even better seen like that. This is the electron diffraction pattern of an alloy of titanium and nickel. Okay, so this is not for graphite, but this is for titanium and nickel. So we made a very thin slice of that alloy, and we shot electrons through it, and the electrons may give us a behavior like this. So you can see it very well that this gives us a pretty weird idea, because you can consider that all these bright spots represent maximals. All of these missing out light spots where the electrons apparently did not match out work as minimals. I mean, if electrons who did behave as an exclusive particle, they did not behave as waves, then they would essentially go in a straight line, and only the center of this fluorescent, not fluorescent, phosphorescent, fluorescent, fluorescent. Only the center of this fluorescent screen should be illuminated. But that's not the case. Electrons have been diffracted or bent in all directions in circular pattern, and we have an illumination like this, or for alloy, we have a behavior like this. So electrons are actually bending outwards. This is representation of that electrons can also behave as waves, which is experimentally provable. And by measuring how much gap is there between individual maximas and minimas, we can go for the equation for diffraction grating, which is diffraction grating a formula d sin theta equals to n lambda, or we can use the we shouldn't be using the formula for double slit experiment because we have a lot of sources over here. So different works better. D sin theta equals to n lambda. We can use that to calculate out what exact lambda is the electron behaving to as a wave over here. And interesting enough, if we calculate the actual speed of the electrons by using the kilovolt source over here, which we can as the energy provided from the electric field is equals to half mv squared. We know the mass of the electron. We can calculate out the speed over here, and we can actually calculate out the momentum of the electron as they're coming out from this electron gun. And if we place those variables into the de Broglie equation, lambda equals to h by p, it matches perfectly, which goes ahead and to prove that his equation is absolutely correct. I do not know that how he came up with this equation. I haven't found it anywhere. I didn't actually look up for it as well. I just see that this very simple equation pop up in the discussion, and its proof is given. But what is the historical background for how this person brain could actually produce a formula of this much simplicity that actually covers that much complication? I have no clue. You might as well look into this as a historical curiosity, if you may. Yes, Abhias, go ahead.
Sir, the titanium diffraction pattern, is it produced by replacing the graphite with titanium?
Yeah, we just replaced the graphite sheet with a very thin slice of that alloy. The idea is that if it's a well-made alloy, in a proper alloy, the atoms actually rearrange themselves so that they can have the least energetic stage with respect to each other. So they will be most stable with each other. So you can have some very specific shape of the orientation, like rhombohedral, tetrahedral, hexagonal, pyramid shape, and there are many different lattice structure shapes. But this, for a very specific alloy of this titanium and nickel, gave rise to this kind of a nice behavior for the electron diffraction. It is important.
So what's the need for to do this diffraction part? patterns.
What is the need?
Like, why are we doing this? We're just trying to prove the de Broglie equation, right?
It can go both ways. First of all, if you do not believe de Broglie equation, this experiment can go ahead and prove to you the actual de Broglie equation is correct. That's one way to look at it. The other way, let's say you believe de Broglie equation and you're trying to do some experiment on this alloy. You get this diffraction pattern view, and then you can measure this whole thing. And from this equation, from this figure, you can calculate the d, which was the diffraction getting constant. And measuring that d can help you to find out the atomic structure of that alloy. So it can go both ways. Bucho.
So the help of the de Broglie equation with the connection of momentum and wavelength, it can help to find atomic structures of substances, sir.
That's one use. Yes. So yeah, that's that. We usually don't use the word momentum with and wave in the same sentence or in the same phrase. Whenever we use the term momentum, we usually say that the momentum of the photon. But whenever we say that the wavelength, we usually say the wavelength of the electromagnetic wave. We rarely use those two terms at the same time unless we are very much sure that we are talking about the wave particle duality. For example, if you're trying to describe the wave particle duality, you can say that a photon can have a wavelength. That works. But typically, you use the term momentum with photon because this is mass and velocity. So photon that works better considering the light as a particle. Or if you're using the word wavelength, we usually say that the electromagnetic wave has a wavelength. But to be honest, they can both have it. I mean, an electromagnetic wave can have momentum, and also a photon can have wavelength. So it actually goes vice versa because wave particle duality is actually a thing which we can prove, and this is the experimental proof for that thing. This is the structure for a giant molecule DNA reduced from electron diffraction. So the shape of the DNA or the bihelix shape of the DNA was actually found out by the electron diffraction. Or electron microscope is a very special type of microscope where we actually shoot electrons onto a thing, and then we can see how the electrons are reflected off. So this can help us to observe stuffs which are actually very, very small, because we can actually control. Have a look over here. The lambda equation the lambda of a certain electron can be controlled by how much momentum do you give it. So the bigger the momentum, the smaller the lambda. So if you excite an electron using the electron gun to multiple different value of wavelengths, it will allow you to see objects with multiple different sizes. If you want to see very small things, you might as well excite the electrons a bit higher so that their lambdas will be pretty small, so that you can see even smaller objects. So electron microscopes are, so far I know, are the most precision microscopes that we human beings have developed so far, using which we can see extremely small, for example, nano level structures very visibly. There is a certain video of some artery video where they work with the butterfly wings. You might as well look that up if you are interested about how an electron microscope works. It's really interesting, and it's amazing what these guys proved.
You showed it in class once, sir.
I did. About
Yeah,
so yeah, I'm talking about
the nanostructure.
the nanostructure in the butterfly wings. I was mesmerized by that video, like, oh my god. So that was the idea for the electron diffraction, and then we have proving the matter, and that's pretty much the equation. So I might as well start to do some discussion for the worksheet. We have about 34 minutes left. I'll take a 5 minutes break to go somewhere. Hold on, 5 minutes break. I'll come back with the worksheets. So I'm resuming the recording, and then I'd like to have the mark scheme as well. So photosensitive effect is here. So let's have a look at question number 1. Electrons emitted from a metal surface which is 100 centimeter with a suitable automatic radiation, and the effect of the discovered photoelectric effect. You cannot do spelling mistake. If you do spelling mistake, you are going to lose mark. The variation with frequency F of the maximum kinetic energy of the emitted electron is 20 7.1. Beautiful. We have some dots. We have the energy with the 10 to the minus 19 scale and frequency with the 10 to the 14 hertz scale. This is 0 graph. Works good. Use figure 5.1 to determine the threshold frequency of the radiation. So all that you have to do is to join these lines. They're pretty much straight, and you can find it somewhere over here, and that value into 10 to the power 14. You have to write that part. You cannot skip this part. Would be your answer. A value for the Planck constant, which will be the gradient of this line. You cannot write the exact value that you know already. You have to essentially calculate that by drawing a triangle and calculating this energy delta y by delta x from this equation, which will be the value of the Planck constant, which is the gradient of the straight line of the kinetic energy versus frequency graph, which we showed earlier. On 7.1, draw a line to show the variation with frequency of a maximum kinetic energy of the emitted electrons for a second metal, which is a lower work function than B. So if it has a lower work function, which means its threshold frequency will be lower. So if let's say, sorry, this electron comes over here, you have to start the new line somewhere on the left side, but not on the zero. And you have to draw a perfectly parallel line with this one. Anywhere on the left is good. Anywhere on the left is good, but it has to be visibly parallel with this original line. So that's that. The kinetic energy of these electrons is described as maximum, says why the emitted electrons are likely to have a range of values of kinetic energy for any one frequency of electromagnetic radiation. So this we know. This is because some electrons, all the electrons are not emitted from the surface level. Some electrons are emitted from the underneath levels as well. But we're going to see what is the wording for the mark scheme that the examiners prefer. Have a look. Maximum correspond to the electrons emitted from surface. Other electrons require energy to be brought to the surface. Pretty straightforward. If you have a look at the examiner's report, it was expected that candidates would realize that when an electron interacts with a photon on the surface of a metal, the electrons will have maximum kinetic energy. The electron has less than this maximum energy when the interaction takes below the surface. Three answers were along these lines. Despite being told in the question that the radiation of one frequency only, most attempted an explanation in terms of a range of in this incident frequency. So apparently, according to the examiner's report, the students or most of the candidates did not know how to address this question, and they might have lost the mark. I'm going through my discussion. If you have any question, raise your hand, or just raise your hand preferably, so that I can give you the floor to give me some explanation. State the de Broglie equation relation explaining any symbols you use. So you have to write the formula, and you have to write lambda equals to h by mv, or you can write h by p directly, and then you can write lambda equals to the wavelength of the particle, and h is the Planck's constant, and p is the momentum of the particle. I'd like to see this thing identified. The correct expression was given by Moscow. However, Manfredi wrote down the momentum as mc, giving the m as the mass of the photon and c as the speed of light. Most referred too simply to wavelength, momentum, and the Planck constant, and did not consider wave particle duality. So, did not consider wave particle duality means that in your description you have to write the combined terms. So, you have to write that in lambda you have to write the wavelength of the particle. In the v, you have to write the speed of the particle. So, whenever you write wavelength of the particle, you are basically considering the wave particle duality within your description. So that has to be included in your identification of this quantity. An electron of mass m is generating a kinetic energy E, show that the de Broglie equation lambda of the electron is given by this much. So this can be done pretty easily. Here we are basically trying to show that P equals to root over 2m, and that's easily doable. I'm going to show you this conversion, maybe on the right side, all the way up. So kinetic energy, which is represented here as E, equals to say half mv squared. I want to express this thing in terms of P somehow. So I want to have half mv whole square. The reason I want this is so that I can replace this whole thing as P. Because I have an additional m compared to over here, I'm going to place one m at the denominator side so that they cancel out each other. I have the same expression. So from here I can write P square by 2m. Therefore, P square equals to 2me, and then it goes P equals to root over of 2me. This is a basic conversion that you are asked to show in this thing, and then you replace the P in the equation, and you get that beautiful equation. This is a pretty useful equation. For a useful version of the original equation can be used for a lot of other calculations. Have a look. Calculate the potential difference through which an electron initially at rest must be accelerated so that the de Broglie wavelength is equal to 0.40 nanometer, the diameter of an atom. Read the question carefully. Calculate the potential difference through which an electron initially at rest must be accelerated, which means we are trying to find out the energy supplied to we're trying to find out the voltage that will supply the energy to the electron, which will make the de Broglie wavelength nearly equal to this one. So here we have to replace the E in some version of voltage. Now you have to remember that the basic definition of voltage is given. Basic definition of voltage is V equals to E by Q, energy over charge. So if I give E equals to VQ. So in this equation, we're going to replace the E as VQ. So our original equation was lambda equals to H divided by root over of 2me. So replace that by H divided by root over of 2m into VQ. So in this equation, H is a constant that we know. Lambda is already given to us. M is the mass of an electron, which is available in a formula sheet. Q is the charge of an electron or elementary charge per se. This is also available in your equation. The only unknown is V. So work with the equation, find out the value of the V. That works.
Sir, question try about that.
Sure. Why does it say my internet connection is unstable? What is happening? This is not. This was not Carlos Menecia. This was Gabriel Iglesias. Iglesias with an I. বুঝা গেছে?
Ji sir.
All right. Number 3, explain what is meant by a photon. This is a pretty interesting question. Before I show you the mark scheme, how do you approach this question? Give me some ideas. 36 people, 35 people. Explain what is meant by a photon. What do you understand by a photon? What do you mean by photon?
So discrete packets of energy transmitted from a light source.
Sounds about correct. Any other idea? Packet of energy or lump of energy is pretty much defining. I think that pretty much works. As well, packet or discrete quantity of packet discrete quantity of energy of EM radiation. Yeah, beautiful. Although most of the answers seem to be referenced by a quantum or packet of energy, many did not include the mention of electromagnetic radiation. Exactly. So this part is what the examiners were missing out on. Indeed, some identified the photon as the electron. Okay, that's wrong.
Sir, do we have to specifically mention electromagnetic radiation? I'm just light বললে হবে.
The reason the word light is less acceptable because whenever we use the term light, we usually mean the visible part of the electromagnetic spectrum. Whenever we say electromagnetic radiation, it means the whole thing, all the way from gamma to radio waves. But whenever we use the term light, typically it only means exclusively the visible spectrum. So they have used a much bigger, broader version because actually photon is basically all over, not exclusive for the light source. So if you use light, it wouldn't be incorrect, but it would be less correct.
Okay, sir.
বুঝা গেছে?
স্যার ফোটন তো ইলেকট্রন না
Yeah, photon in electron না ওই জন্য indeed বলছে. This is wrong. This is one of some of the most common mistakes that the examiners found out. You are not supposed to do this. Then it says show that the photon energy of light wavelength is this much. This is just very E equals to HF equation. You can find this out. State the value of the ratio of energy of photon of light of atto divided by atto. This is just gonna be 2. You're not even expected to do any calculation over here because E equals to HF. No, so this is gonna be half. এখানে ওয়েভলেন্থ দিয়ে করছে না তোমরা অবশ্য বুঝো
স্যার
সো আমাদের কোর ইকুয়েশনটা হচ্ছে কিরকম যদি ওয়েভলেন্থ দিয়ে দেখি let me show you আমাদের কোর ইকুয়েশনটা হচ্ছে E equals to HF or I can write this as E equals to H C by lambda. So E and lambdas are inversely proportional. So if we're trying to find out the energy variation between energy of 700 nanometer of lambda divided by energy of 350 nanometer of lambda. So the ratio of wavelengths would be opposite to the ratio of energy, because lambda is on the bottom side. So this would give you 2 over here, 1 over here. That's why they didn't give any space for calculation, because they are expecting you to not to do any calculation for this one, just be able to use the idea of proportionality and not mess up the ratio. So 0.5. An explanation for this one, as expected, the answer was 0.5 and 2.0 were seen in approximately equal numbers. Okay. As expected. The examiners are cruel people. Anyway, I don't mind saying this, but this part, as expected, is actually pretty mind-boggling. Do you guys understand why? The examiners knew.
They expect.
Yeah, the examiners knew. Kids are gonna mess this up. Some people are gonna give half, who actually knew the opposite inverse proportional relationship. Some kids are gonna give directly 2.0, because I initially said 2.0. Then it popped my hand. Oh no. Equals to HF. Lambda goes at the bottom, so it's gonna be half. So initially I said 2.0, which is the initial response. Yeah, why not? Good for them. Two beams of monochromatic light have similar intensity. এই কোশ্চেনটা ভালো করে খেয়াল করো। Two beams of monochromatic light have similar intensities, which means energy per second per unit square area is equal. The light from one beam has wavelength of 50 nanometer. The light in the other beam has wavelength 700 nanometer. The two beams are incident separately on 3 different metal surfaces, so one at a time, separately. The work function of each of these surfaces are shown in figure 5.1. So if metal, we have work function. Explain what is meant by the term work function of the surface. So how do you explain this term?
The minimum energy
Required. Yeah, go ahead.
Energy required for photoelectric emission to occur.
For a photoelectric emission. So the key term is minimum. That is very important. And photoelectric emission to occur, I think, is the second.
Can we also say that it's the minimum energy required to make an instantaneous jump to an infinite orbital or infinite shell?
We can. That's not incorrect, but that it would be, I say, too much precise. But that you might as well write that. If you write that, and if I was the examiner, I would give you the marks. But because it's perfect, have a look. It has a lot of expression over here. কত নম্বর ছিল এটা জানো? This was 3B1. Energy of photon to cause emission of electron from surface, or either with 0K or photon energy is minimum. Okay. So minimum energy of photon to cause an electron from surface. Okay. From surface it has to be mentioned. Yeah, this is pretty important, because আমি work function explain করছি from surface বলি নাই, because you have to understand that from surface you gonna require the smallest amount of energy by basic understanding. So if you're trying to define work function, the amount of energy that would be used to emit an electron from the exact surface would be the work function. That's why from surface was underlined. So if you miss out this much phrase, you'll be losing 1 mark, which I would. If I was answering this question, I would not be writing from surface, but now I am alerted about this one. Let's have a look at the mark scheme. It was expected that candidates would make a reference to the minimum energy required to remove an electron from the surface of the metal. Of those answers that were recognizable as being concerned with the photoelectric emission, many did not include a mention of minimum energy. So in the examiner's report, they are highlighting on the term of minimum, but in the mark scheme, they have underlined the term from surface. So please do mention that.
আচ্ছা, আমরা তো দেখেছিলাম it can also take place from an inner electron, not necessarily surface যে থাকতে হবে.
Exactly. It can happen for an inner electron, but if you want to release an electron from the inside, you have to supply a photon bigger than the work function. We're trying to define work function here. So the minimum amount of energy which would be actually capable to make an electron release from the metal piece should happen at the surface exclusively. বুঝছো?
Yes, sir.
So then it says, this is a very interesting question. State which combination, if any, of monochromatic light and metal surface could give rise to photoelectric emission. Give a quantitative explanation to your answer. আচ্ছা, এই কোশ্চেনটা আনসার করার দুটো ডিফারেন্ট উপায় আছে. I'm going to show you both the ways, but you can choose, or you can see which one is more elaborate, which one is less elaborate. Try to understand the question first. State which combination, if any, of monochromatic light and metal surface could give rise to photoelectric emission. তার মানে হচ্ছে আমরা যখন এই দুটো ডিফারেন্ট ওয়েভলেন্থের লাইট আমরা এই মেটালগুলোর উপরে শাইন করব, কোন কেসে or কোন which pair means light source and metal is gonna give us photoelectric emission. So there are two different ways we can go by. একটা উপায় হচ্ছে we can find out the individual wavelength, threshold wavelength. Threshold wavelength should not be a threshold wavelength. I mean, we can find out the threshold frequency of these individual metals and convert those things into wavelengths and then compare that which one is which. So we can either find out their relevant lambdas and compare them with 350 and 700. That's one way to go. The other way to go is that we can calculate how much energy does each of these photon contain and then convert those energies into electron volt, because these things are given into electron volt, and compare all of this and compare these electron volts with this one to find out which one is big, which one is small. So I'm going to do the second method first and then the first method second, because that's easier for me to attempt. So let me just copy this question. I might as well have this question copied. So the first thing first, let's try to convert the wavelengths into that part. So let's say I have some space available. So energy of 350 nanometer equals to 6.63 into 10 to the power 34 into 3 into 10 to the power 8 divided by 350 into ন্যানো হচ্ছে 10 to the minus 9, ঠিক আছে? হিসাব করে দেখাও তো এটা কত আসে?
5.68 into 10 to the power minus 19.
আচ্ছা, কিছু একটা আসবে। আমি একই সাথে এটাকে আবার ইলেকট্রনের চার্জ দিয়ে ডিভাইড করে দিচ্ছি। কেন? Because I want to get the answer in electron volt. I want to get the answer in electron volt. I want to compare with directly with these numbers.
So 3.55.
3.55, sir.
5 এর পরের ডিজিট কত?
1.
আচ্ছা, so এটা 3.55 আসছে। Honestly speaking, if I get this one to be 3.55, keep the calculator value over there. Don't press on. Don't press on. I can logically say that the energy of the 700 nanometer would be exactly half of this. Do you understand why?
Because lambda is doubled.
Because lambda is double, and we actually calculate that value over here. So we can simply divide that by number by 2. So we can write over here 3.55 electron volt divided by 2. If you do this, you're going to get full mass for this, by the way. How much do you get? Divide that calculator value by 2.
1.776.
So 1.78 electron volt. So these are the two irrelevant electron volt energies or photon energies which are coming in from. Now have a look between these two energies and between these three metals. Let's see for one by one. This one cannot make let me use two different color. Maybe let's say for the first one, I'm going to use let's say red. So I'm going to use red for this one. This amount of energy cannot make for this one, cannot make for this one, can make for this one. You do understand why? Because
Yes,
the
sir.
photon energy has to be bigger than the work function, or at least has to be equal to the work function for the at the very least. If you use blue for the next one, let's say I'm using blue for the next one. So 1.78 electron volt cannot do for this, cannot do for this, cannot do for this. So there is only one pair left. So you can say that only the light wave of 350 nanometer paired with potassium can give us photoelectric emission, because the photon energy is bigger than the work function of potassium. The question says that the work function of this did the what is the question? Statistical give a qualitative explanation. Yeah, qualitative explanation. Because they are demanding an explanation, that's why you should write the last sentence that I said, that because the photon energy is bigger than the work function of potassium. So you should write that sentence as well. So this I find to be the simplest method to go for. Alternately, what you could do, convert all of these things into relevant wavelengths, or which, did we do this in this question or did we do this some other question? Okay, never mind. So have a look. Understand the second method. Lambda equals to hf or hc by lambda. So কি লিখতেছি আমি? Energy of a photon equals to hc by lambda. সেখান থেকে যদি আমি ল্যামডাকে সাবজেক্ট করি, I'm gonna get what? hc by e. So this would be basically, so I can find out that for lambda of tungsten, হবে হচ্ছে 6.63 10 to the power minus 34 into 3 into 10 to the power 8 divided by 4.49 into 10 to the power into 1.6 into 10 to the power minus 19. এখান থেকে দেখো ল্যামডাটা কত আসে, calculate this value, write this whole thing in this fraction form. It will be easier for you to do the next maths easily. এই যেভাবে দেখতেছো তোমাদের ন্যাচারাল ডিসপ্লে ক্যালকুলেটর ইজিলি এইভাবে লেখো, কারণ এরপর আমি জাস্ট এই ভ্যালুটাকে চেঞ্জ করব, আরেকটা পাবো, আবার এটাকে চেঞ্জ করে দেবো, আরেকটা পাবো। সো রাইট দিস ইন দিস এক্সাক্ট ফর্ম and see how much do you get from here. Anyone?
Sir, 4.49 কেন?
I'm trying for tungsten first.
Sorry, it's 2.769 into 10 to the power minus 7.
Convert that into nano so that I can write this in nano. So have the 10 to the power minus 9. Press shift engineering, shift eng. It will shift your decimal.
Sorry, then it's 276.9.
276.9 nanometer. Okay, now in this whole expression, just replace this number with 3.68 and find out magnesium.
Sorry, it's 337.8.
And then for potassium,
So 550.
5. So now you can go ahead for a reverse comparison, that you can say that only the potassium has a required wavelength that is bigger than the 350 nanometer. So these two will give you the rise to the photoelectric emission. Other pairs would not. But I personally don't like this mechanism, but this is also an acceptable way to go for it. It's equally mark scoring, but I personally don't like it very much. I like this one better because here you are directly comparing the energies. That makes a better explanation. But you can go for this one as well if you want. I'm just showing you to convince you of that there are two different ways to approach this problem. বুঝে গেছে সবার?
জি স্যার।
Any question? Anyone?
Sorry, এই পার্টটা একটু আরেকবার রিপিট করবেন, লাইক যে ওয়েভলেন্থটা কিভাবে ইন্টারপ্রেট করবেন?
বলতেছি, you have to understand that the smaller wavelength will give you more bigger energy. So আমাদের আইডিয়া ছিল হচ্ছে ফ্রিকোয়েন্সি, আইডিয়াটা ছিল হচ্ছে থ্রেশহোল্ড ফ্রিকোয়েন্সি। সো ল্যামডা আইডিয়াটা হবে হচ্ছে ম্যাক্সিমাম ল্যামডা। So the one that has bigger lambda values would be able to give you that energy. So for example, for potassium, if we shine up light of 350 nanometer onto this surface, this would give me photoelectric emission because this is smaller. This would not, because the required wavelength for photoelectric emissions to start for magnesium is bigger than 350. It's definitely bigger than 700, so I'm not talking about that at all. So magnesium with 350 would not give you photoelectric emission because 350 nanometer photons would not have enough energy to make the work function. Similarly for this one as well. Bucho?
Yes, sir, got it. It's the opposite.
It's the opposite of the frequency revolution, yes.
It's easier to get confused with this one, sir.
Exactly. It's very easy to get confused with this one, or writing the proper word in proper sense making way, it is very difficult as well. I personally like this one. This is less calculation and easier to make sense as well. So just convert the wavelengths into energy so you can really compare the energies, and it's easier. The left side is easier. Then we have explain why for the আচ্ছা আমি জাম্প করে কিছু কোশ্চেন একটা ব্যান্ড থিওরি একটা কোশ্চেন বের করতে যাচ্ছি, so you can do some calculation about that. Should this be a good one? I think this can be a good one. Okay, let's try this one. Explain how a line spectrum leads to an understanding of the existence of the discrete electron energy levels in atoms. 3 marks. Question দেখো. Explain how a line emission spectrum leads to an understanding of the existence of discrete energy levels in atoms. So line spectrum থেকে কিভাবে আমরা discrete energy level কে decide করতে পারি? How does this observation, line spectrum, leads back to the discrete energy levels? So if we go for, I could actually explain this to you, but I have already done that. So I'm gonna go look out for the exact wording that the examiners are looking for. 9A. Each line corresponds to a specific photon energy. Okay. Photon emitted when electron changes its energy level. Photon emitted when electron changes its energy level. Okay, that's also correct. Actually, electron comes back to a lower level, but they only use the term changes. Okay, I'm cool with it. Discrete energy changes, so discrete levels. Okay. Let me elaborate this Marcin a little bit. What they're trying to say is that in your writing, you should have a couple of points highlighted or exclusively mentioned. Each photon emitted represents a fixed amount of energy, or you can use the discrete. Each energetic photon is released whenever electrons jump back to a lower shell. Because discrete values of photons are released, that's why the shells have to be also discrete. বুঝছো কি?
Sir, question টা একবার দেখাবেন?
Sure.
Sir, so we are trying to say that since like different level of give different energy photons, which this means that we have different levels of energy in this atom.
Exactly. I mean, if I try to fill the void of this information, which is not necessarily right, but can be helpful for you to understand better, সেটা হচ্ছে if energy shells were not discrete or were not different, মানে definite and different from each other, if it was like a continuous energy form, then the emitted photons would be emitted at all the possible wavelengths and frequencies. But we don't get that. One specific metal or one specific specimen gives very specific values of photon energy, because we have jumps from electron transition from one level to another, and because the levels are discrete, that's why the photon energy that we get from a single metal, they are also discrete. Do you get my point?
Yes.
When I try to explain what is on the other side, what could possibly be on the other side of the discussion, that if the shells were not discrete, then one single atom or one single metal specimen would be able to give a continuous spectrum. But we do not get continuous spectrum, we get line spectrum, proving that the shells are different from each other / discrete from each other. বুঝছো?
Yes, sir.
Sir, could you just use the reverse argument to explain the answer, or do we have to directly explain that?
No, you don't have to use the reverse argument. I'm telling you the reverse argument to help you better understand. You should not even write that reverse argument. I'm telling you the reverse argument to help you better understand the problem, that what would have been if the other thing was available. Because the other thing doesn't happen, so this thing has to be correct. That's why I'm telling you the reverse argument. You don't have to write that. I'm just trying to give you a better idea.
Okay. I actually find the reverse argument pretty clear, sir. That's why I'm asking.
Acha, okay. Well, use the reverse idea to understand it better, but write the appropriate argument that the examiners are looking out for. That's one way I can put this down. Holy crap. Oh, not this. Oh, wait. না, good. আচ্ছা, আমি এই পরে ম্যাথটা করতে যাচ্ছিলাম, তারপর আমি তোমাদের ক্লাস ছেড়ে দিব। একটু এই ম্যাথটা একটু দেখি। Some of the lines of the emission spectrum of atomic hydrogen are shown in figure 7.1. So we have these atomic level lines. The photon energy associated with some of these lines are shown in figure 7.2. Wavelength, photon energy, blah blah blah. So আমাদেরকে এই এনার্জিটা ফিল আপ করতে বলছে। 486 এর জন্য এনার্জি কত হবে? In with a multiple of 10 to the minus 90. এটা ক্যালকুলেট করো তাতেই। Just do it.
স্যার এটা কি যে E equals to HF দিয়ে?
Definitely.
Sir, 4.09.
আচ্ছা, ন্যানো ইউজ করছো? এখানে কিন্তু ন্যানো
Yes,
আছে,
sir.
ন্যানোটা ইউজ করা লাগবে, না
Yes,
কিন্তু
sir.
10 এর পাওয়ার মিলবে
10
না।
to the power minus 9 will multiply করেছি। 4.09 into the power 10 to the power minus 19.
আচ্ছা, সো এখানে আসবে হচ্ছে, oops, my page, I ran out of page. That shouldn't have happened. সো এখানে আসবে হচ্ছে কত বললাম? 400
4.09.
4.09 আসছে। আচ্ছা ঠিক আছে, এটা গেল। এরপরে কোশ্চেন আমাদেরকে বলছে হচ্ছে Goblet figure 7.2 by calculating the photon energy of for a wavelength of 486 nanometers. So এই ক্যালকুলেশনটা এখানে করতে হবে, ভ্যালুটা এখানে বসাতে হবে। ভ্যালুটা কি এখানে বসাতে বলা নাই, বলছে কি? বলে নাই। সো এই জাস্ট এখানে ক্যালকুলেট করতে বলছে। আচ্ছা না, কমপ্লিট ফিগার 7.2 হ্যাঁ বসাতে বলছে। সেখানে ক্যালকুলেটও করা লাগবে, এখানে বসাইতে হবে। সো ইউ হ্যাভ টু ডু বোথ। Then it says energy levels of a single electron in a hydrogen atom is shown in figure 7.2. So this is the energy deviation for shell 1, shell 2, and it goes up value upwards. Use data from figure 1 to show on figure 7.3 the transition associated with each of the 4 spectral lines in figure 7.1. Show each transition with an arrow. So that means what is happening. Some of the lines of the emission spectrum. Have a look. Emission spectrum. Emission spectrum means what? The photons are released or photons are absorbed.
Photons were released.
Photons are released. So the jump of electrons should happen upwards or downwards.
Upwards.
Photons are released when electrons get excited or de-excited.
Sir, DXI.
Excited.
Photons are absorbed. Energy is absorbed when they are excited.
Yes, sir.
When they are de-excited or they are coming back from the excited shell, then photons are released from the atom. So since this is an emission spectra, so all the arrows that we are about to draw over here should be downwards. That's the first thing. And then we have to somehow relate this energy's amount over here. So I will take this image and try to fill this up with the help of this table. আচ্ছা, এটা এখানে প্লেস করি, might as well be helpful for me. Okay, have a look. এখানে আমরা খেয়াল করি যে এখানে আমাদেরকে বলছে আচ্ছা, এখানে আমাদের কোন লাইনটা কি সেটা আমাদের লেবেল করতে হবে না, জাস্ট ভ্যালুগুলো বলতে বলছে। So have a look. We are gonna try to find out that what jump gives us these values. To be able to find out these values, we might as well consider that no electron is jumping back to the second shell. Sorry, first shell. Because you can, what is the energy gap over here? Do you see? How big is this? Pretty big. None of these energy values over here correspond to this. But anyway, if you still are skeptic about this, I can help you to understand this thing. Find out the difference of these levels. This is the first thing that we need to do. And you might as well do this in your exam as well. Find out the difference of these levels. এটা হচ্ছে কত? 0.27. এটা কত? These two.
Uh, 0.49.
তারপর
1.06.
1.06, তারপর 3.03. এটা অবশ্য না করলেও হয়, বাট স্টিল জাস্ট বিকজ উই আর ডুইং এটা কত 35 16
16.35.
সো আমরা এই ভ্যালুগুলো পাইলাম। এখন তুমি দেখো যে আমরা 3.03 এর জন্য একটা জাম্প পাচ্ছি। So we might as well draw this first. So this thing is gonna give us. So I'm first doing this one because I can see it very well available here. So a downward arrow, you have to give the arrow direction. Otherwise, this will not make sense. This is an released photon. This might as well mean there is an absorption photon. Okay. Then we have 4.09. So try to add up multiple values to get for which jump you get 4.09. এই দুটাকে অ্যাড করলে কত?
1.06 plus 3.03, 4.09.
This addition of these two gives you 4.09.
4.09.
We found this one. We as well found out this one. So this one will be this one. Use ruler, preferably. Then you add these three. See how much you get. Add these three. You should get 4.58,
1.58.
which means this. And then if you add all of these, you're going to get 4.85. So in this case, we are having the possible jumps all the way up to the second shell and not any more further down. So that's what the question is essentially giving us. So these are the lines that we are getting for hydrogen spectrum. But obviously, we're going to get some line for the lower part, but that was not shown in our question, so we don't bother about that. Because you can see over here, it says very clearly some of the lines of the emission spectrum of atomic hydrogen, not all the lines, because you do understand electrons should not stay over here. Ultimately, electrons are going to come back to their original shell, which is the shell number 1. So that's how we do this. If any of these numbers were, let's say, if an electron, let me ask you this: if an electron jumped, let me draw with an arrow, and I might as well zoom on this one so that you can see a better view. This have seen this much part is good. If an electron made a jump from here to here, how much energy should that be labeled in that question?
$1.46.
It will. No, you have to add them up. 1.06 plus 0.49 gives you 1.55.
1.55. I mispressed.
So if an electron jumped from here to here, this would emit an photon equivalent of 1.55 into 10 to the minus 19 joule. So that's basically about the calculation about the arrowheads that you are about to draw for multiple cases. এরকম question আরো অনেকগুলি আছে. If you go down into the PDF, you will find a lot of questions are of this type. You have to be careful about one factor very precisely. Is that are we talking about emission spectrum or are we talking about absorption spectrum? If it is emission spectrum, always arrows have to be downwards because electrons are going to be coming to their lower shell. If the question says absorption spectrum or absorption case, then the electrons are going to go upwards. Absorption cases are pretty rare. Maybe they are, let's say, 5% of the whole of this kind of questions. But it is possible that sometimes they can say that electrons are absorbing energy in the absorption chamber. So if it says absorption, electrons are going to jump up. If it is emission, electrons are going to jump down. That's the key part that you cannot mess up. Calculation part is pretty simple. It's just addition and subtraction, and that much I think is easily doable, I believe. At this point, we're going to conclude today's class. I'll upload this PDF in a short while to you and also the lecture to the YouTube channel as well. আর হচ্ছে আমি একটু পরে তোমাদেরকে চ্যানেলে লিখে দিব যে কালকে যদি কেউ বুকলেট কালেক্ট করতে চাও তাহলে করার সময় আসতে পারবা। আর যারা ঢাকার বাইরে আসো, I want your booklets to be collected. Please send a message to my Facebook page. There is a Facebook page, not my messenger channel, not my profile, Facebook page. I have a Fasisafi's Facebook page with your name, your full email address. I mean name, care of, full email address, যেটা delivery man এর দিলে তারা তোমাদের বাসায় পৌঁছে দিতে পারবে. So I'll be sending out the delivery either by Pathao or by Sundaban Courier Service, and you can have it, let's say, within 2 or 3 working days, hopefully. Thank you very much. Good night.
Sir, timing কি সেম কালকে?
আমি এটা একটু পরে তোমাদের চ্যানেলে পোস্ট করে দিচ্ছি, মেসেঞ্জার গ্রুপে পোস্ট করে দিচ্ছি।
আচ্ছা স্যার।